Breaking the rules, planetary physics reimagined. How does a planet like WASP 76b force scientists to rewrite the rules of what planets can be? For most of human history, our concept of what constitutes a planet was limited to the examples in our own solar system. From Mercury to Neptune, our planetary neighbors provided the framework for how we understood worlds beyond Earth. These planets follow certain patterns: rocky inner worlds, gas giants farther out, all orbiting at relatively comfortable distances from the Sun. They established what seemed like universal rules for planetary formation and structure. Then astronomers discovered WASP 76b and other ultra-hot Jupiter's planets that shattered our cosmic rulebook. These worlds exist in physical regimes with no equivalent in our solar system, creating environments so extreme they were previously considered impossible. The discovery of these planets represents a fundamental shift in our understanding of planetary science, forcing the complete reimagining of what planets can be. Ultra-hot Jupiters like WASP 76b challenge traditional planetary classification systems in fundamental ways. Our classic divisions between terrestrial planets and gas giants fail to capture the nature of these worlds. While they have masses similar to Jupiter, their proximity to their stars creates conditions unlike anything in our solar system. The extreme heat transforms their atmospheres and alters basic physical processes, creating a category of planets that don't fit neatly into our established frameworks. These planets defy conventional formation theories. Standard models suggest that gas giants form beyond the snow line in a stellar system. The distance from a star where water can exist is ice. Finding Jupiter-sized planets orbiting just a few million miles from their stars raises profound questions about how these worlds formed. Did they migrate inward from more distant orbits? Did they form in place through mechanisms we don't yet understand? Either answer requires significant revisions to planetary formation models. The most dramatic way WASP 76b breaks planetary rules involves its atmospheric chemistry. Under Earth conditions, elements like iron, titanium, and magnesium exist as solid metals. On WASP 76b, temperatures reach over 4,350 degrees Fahrenheit, 2,400 degrees Celsius, hot enough to vaporize these metals. This creates an atmosphere containing gaseous metals that would never exist as gases under conditions found anywhere in our solar system. The chemistry occurring in WASP 76b's atmosphere simply doesn't exist in any natural environment on Earth. These extreme conditions create possibilities for exotic compounds and chemical reactions that can't occur elsewhere. The planet becomes a natural laboratory for studying how matter behaves under extraordinary temperature and pressure regimes. Chemical bonds that remain stable on Earth break apart or form in new ways on WASP 76b. Elements interact in combinations impossible under cooler conditions. This extreme chemistry forces scientists to expand their understanding of how atmospheric processes work on planets throughout the universe. To account for the strange worlds, scientists are developing entirely new atmospheric models specifically for ultra-hot Jupiters. Traditional models assume temperature ranges and chemical compositions similar to what we observe in our solar system. These new models must account for gaseous metals, extreme temperature gradients, supersonic winds, and other phenomena unique to ultra-hot Jupiters. Each new discovery about WASP 76b's atmosphere necessitates further refinements to these specialized models. Perhaps the most perplexing question WASP 76b raises involves planetary migration. How did this massive planet end up so close to its star? The most likely explanation involves a complex journey from a more distant formation location. Gravitational interactions with other planets or with the protoplanetary disk might have altered WASP 76b's orbit, causing it to spiral inward toward its star. As it migrated inward, the increasing heat would have transformed it from a more typical gas giant into the extreme world we observe today. This migration scenario raises questions about the planet's history and evolution. How long has it orbited so close to its star? How much of its original atmosphere has it lost to the extreme conditions? What was WASP 76b like before it migrated inward? The answers would tell us about the general processes that shape planetary systems throughout our galaxy. Some scientists propose an alternative explanation that WASP 76b might have formed in place, very close to its star. This would require a different set of initial conditions than our traditional models assume. If true, this would require a fundamental revision of planetary formation theories, opening new possibilities for how and where planets can develop. By studying extreme worlds like WASP 76b, astronomers gain insights into the boundaries of planetary physics. These planets show us the limits of what's physically possible for a planetary body. They expand our understanding of atmospheric dynamics, thermodynamics, and chemistry under conditions we can't recreate in laboratories. Each new discovery about ultra-hot Jupiters pushes the boundaries of planetary science, forcing revisions to theories that once seemed settled. WASP 76b represents an entirely new category of celestial objects that exist in the borderlands between planets and stars. Too small to ignite fusion reactions, they aren't stars. Yet their extreme temperatures and exotic atmospheric chemistry place them in a different category from the planets in our solar system. They occupy a middle ground, challenging our binary classification of celestial objects and suggesting a continuum of possible worlds. The existence of planets like WASP 76b reminds us that our understanding of the universe remains limited by our experience. Until we discovered these worlds, we assumed planets followed certain rules because those were the only examples we had observed. As our technology improves and we find more exoplanets, we continue to discover worlds that expand our conception of what's possible. Nature consistently shows more creativity in planetary formation than our theories anticipated. As we continue to study WASP 76b and similar planets, each new discovery raises as many questions as it answers. The mystery of iron rain led to the discovery of the Gloria effect, which in turn revealed new details about the atmosphere's structure. What other phenomena remain to be discovered on this bizarre world? What other secrets might it reveal about the fundamental